The first talk is by Professor Sreerup Raychaudhuri from TIFR, and he's going to tell us about reviving the Stueckelberg mechanism.
Okay, good morning everyone. I'd first like to thank the organizers, thank Professor Ravindran and the organizers of this meeting for inviting me to attend and hear these nice talks, to also tell you a little bit about my work, and of course also to pay tribute to my former teacher and to the teacher of many people in the audience here, Professor Amol Raychaudhuri. So I will begin my talk from the back, from this last line. So start with this nice picture. Those who knew AKR will remember this is a very characteristic expression of his when he wanted to explain something. And we also know that AKR didn't like he didn't like too much praise and so on. So I will confine myself to one small tribute. And let's go ahead. But today's talk will not be about AKR. It will be about a work done by a different person, which came 2 years after AKR's famous works. It was first suggested in 1957. And the person I will talk about is Stueckelberg. So ECG Stueckelberg, and he was Baron Stueckelberg, if that helps. So he was a Swiss physicist who is remembered today mostly for proposing the conservation of baryon number, and also for the idea that antiparticles can be treated as particles moving backward in time, which is called the Feynman-Stueckelberg interpretation, which is in every textbook. But Stueckelberg also did a number of many other original things, which he had a habit of publishing in obscure journals which no one read. And so he remained unknown, and his work remained unknown, and many other people got credit for some of these seminal discoveries. Now, why I call them seminal discoveries, I'll give you the list. So he's the first person to write down the perturbation theory for quantum fields, which was sort of credited to others. The first person to write down an exchange force. He used a vector for strong interactions, which Yukawa is credited with. He discovered the abelian Higgs theory in 1938, many years before the well-known people. Completed the renormalization of QED, for which other people got the Nobel Prize. And he had an idea of the renormalization group as early as 1953, long before Wilson. But he had this habit of publishing in an obscure journal called Acta Physica Helvetica, which didn't reach anywhere. And the result is that people only recognized that he had done this work many years after he had actually done it. Anyway, so today I'm going to talk about an idea which he came up with in 1957. Remember, this was just after Schwinger had proposed the intermediate vector boson hypothesis for weak interactions. And of course, these bosons had to have mass. And it had been famously pointed out by Pauli that you can't put mass. So I'll just quickly revise that, and then I'll come to the Stueckelberg mechanism. So senior of mine in university used to say, every talk should begin with F equals MA, or H psi equals E psi. So I will not start quite from there, but also from something which everyone knows. So let me just quickly recall that in an abelian gauge theory, you have a local gauge transformation, and then this is the QED Lagrangian. You write down term with a covariant derivative, which has the gauge field. Gauge field transforms like this, and you write down the kinetic term for the gauge field. And of course, it's famously known that if you want to add a gauge boson mass term that was not gauge invariant, you get these extra terms, and as a result, you must set this coefficient m to 0. That's why you get a massless photon. So that term doesn't exist. Now, Stueckelberg's idea was that let's construct something like a gauge invariant field variable, but add a scalar and construct it like this and ensure that this scalar transforms in a similar way to the gauge field. And then you see what happens. So make this the transfer. When the gauge field goes to mu plus del mu, this guy goes to sigma minus m theta. M is some mass parameter. Let's just introduce to handle the dimensions. Now, look at the transformation. When this one transforms, so the gauge field transfers the mu plus del mu theta, the sigma transforms to sigma minus m theta. Now look at this term, the m's cancel, you get del mu theta with a minus sign, so they cancel. So this object is a gauge invariant object. So now to this QED Lagrangian, you can add a term like this with a mass term and gamma mu. So here is a way to add a mass term without breaking the gauge symmetry. No spontaneous symmetry breaking, you just get a mass term. Okay, let's see where that takes us. So this scalar is called a Stueckelberg scalar. Scalars which transform in this fashion, similar to the adjoint representation, are called Stueckelberg scalars. Now let's expand this Stueckelberg term which I added. So just put in the values. So you'll get three terms. There's an mu term, there's a cross term, and there's a d mu sigma. See, this is the kinetic term for the scalar. And we have this. So now what is happening here? Of course, this gives you the photon mass term. This gives you a massless scalar. There's no scalar mass term here. But on this other hand, there is this bilinear here. So people ask the question, what do we do with this bilinear, and then how do you get rid of this? And at the same time, there is a massless scalar in the theory, and there's no evidence for that anywhere, so what do we do with that? So this led to the early abandonment of the Stueckelberg model. However, it was soon pointed out that you can actually get a mass for the scalar. How do you do that? You construct a gauge invariant like this. So you write down a capital sigma, which is sigma minus, you subtract out a term like this. And this suggestion is due to Pauli. And he wrote a review in which he discussed the Stueckelberg model, and he added this. And typical of Pauli, he didn't write a separate paper about it. He just added it as part of his review. And now what happens is that you can add on an invariant term again with a minus half m squared sigma squared. So let's look at the whole thing. So let's check the gauge invariance of this. Sorry, that's sigma, not sigma. But let's check the gauge invariance. So again, I am putting sigma transforms like this, mu transforms like this. So what you get is sigma minus this object. So there is a dependence on the gauge. But now if you choose the harmonic gauges, where this belongs to, satisfies the Klein-Gaussian equation, then you do have, so if you stay within the family of harmonic gauges, then you do have gauge invariance. So fine, so now let's take the full Lagrangian. We take the QED Lagrangian, add on first, this is the gauge boson mass term, and this is the scalar mass term. So together these two parts are called the Stueckelberg part of the Lagrangian. Okay, so let's take this ahead now. So let's look at these Stueckelberg terms in more detail. So this gamma mu I expand, and this sigma I expand. So this first line is expansion of the gamma mu. Second term is the expansion of sigma mu. Notice that I get bilinears from both these terms. So what happens if I add them? It gives you a total derivative. And you can throw that out of the system. So that's the beauty of this, that when you make this expansion with Stueckelberg, when you put the second term, which is the Pauli contribution, you can get rid of the bilinear. So what is left in the model now? So yeah. So these are gone. So now your full gauge invariant Lagrangian. So see, you have this is the part which I get from QED, this first three terms. Here is a mass term for the photon, and you also, as a bonus, you got a gauge fixing term with xi equals half. So gauge is also getting fixed nicely. And here you have a scalar with a mass. So massive fermion with gauge interactions, a massive gauge boson with gauge fixing inbuilt, and a free massive scalar in the joint representation. So very pretty. The problem here is that the mass of the scalar has to be the same as the mass of the photon. So the photon mass is 0, the photon is a massless scalar, it's back again. If you want to apply to electroweak theory, then the mass of this one will be the W mass, and you will have to get a scalar with the same kind of mass, which you didn't see, and even then you knew it was not there. So this led to the second abandonment of the improved Stueckelberg model. So that's sort of where it is. After that, the Stueckelberg mechanism has been used in various places by various theorists. But the whole idea of this talk is to bring it back where it belongs, to electroweak theory. So let's ask what happens if we combine it with the normal Higgs mechanism. Okay, it looks like overkill because both of them give mass to the thing. But of course, we now know that the Higgs is known to work. The Higgs exists. There is a Higgs boson. So let's see what happens. Now, we can basically ask a different question, not whether the Stueckelberg model can give mass to the Higgs, but to see if there is a scalar belonging to the joint representation like the Stueckelberg. Can it be accommodated in a spontaneous broken model? Let's ask ourselves this question and see how far we can get with that. So here's the Lagrangian of the model. Now, interesting thing is this part is the usual QED part. Here is the spontaneous symmetry breaking potential. And here are the two Stueckelberg terms. But now that you have this gauge invariant combination, you can add on two other terms with two unknown couplings. So these are the usual things. Scalar electrodynamics is the top one. Then this is the potential. And the Stueckelberg terms are fine, but we do have a new thing, that is these new quartic interactions exist. So the moment you combine the two, you'll have to think about these quartic interactions. And as we shall see, these play a very crucial part in making the model useful for a phenomenologically viable model. So after symmetry breaking, what happens? So you shift the scalar field, and also the Stueckelberg field has to be renormalized. You don't get the canonical term for the canonical form of the kinetic term. So if you expand the Stueckelberg section, see this is what we had, right? So here you will get v squared by 2 in place of these. So if you plug those in, you see you get lambda 1 v squared by 2, and the m squared I have pulled out 1. So you can write them in terms of delta 1 here. So there is a photon mass term. This is a bilinear here, and there is a term which has the gauge, the scalar kinematic term, but it has a non-canonical form. And the second one, that comes in terms of delta 2, which is proportional to lambda 2. And again, we get a bilinear. This is your gauge fixing, and this again is your mass term for the scalar. So obviously, you want these two to cancel. But now if you want them to add up to a total derivative, you'll have to set delta 1 equals delta 2. So let's do that. So that means I don't have the freedom to choose this lambda 1 and lambda 2 freely. So I need to choose them equal. So let's call them some delta, and we'll just call this lambda 1, lambda 2, we'll call them lambda prime. So there's one common thing here, lambda 1, lambda prime. And now you have these forms. So now these terms we can get rid of. So what is left? Let's go to the next slide. So I just copied that here. So now if you look at this scalar kinetic term, you see that this thing has to be 1 to have the canonical form. So I choose this wave function normalization, I absorb it in the sigma field, and that's this particular. And now you see that this is different from 1 because of the existence of this extra quadratic coupling. So now you can plug this z back in here and elsewhere. So if you plug this in, you get a photon mass, which is this, again similar to this, and you get a gauge fixing term, which is 1 by the photon mass squared. So these are connected. And remember that this part gives you now the photon, massive part of the photon plus gauge fixing term, and this gives you a massive scalar. All right. And of course, the photon mass, remember, will also have a component from the Higgs. So that is actually E squared V squared plus this term. So the photon mass is not quite, so essentially this is an extra contribution. And the Stueckelberg scalar, now notice something here, now it can have a large mass. Since look at this is the photon mass. So if there is you can arrange for a decent cancellation among these terms, then this mass can be much higher. So the Stueckelberg mass is not confined to be a degenerate with the photon. Where does it come from? It comes one from this new quartic interaction, and also it's because of the symmetry breaking, because if you take V to 0, of course, the masses will go. We didn't have that in the previous model. All right, so what was achieved by this toy model? So first of all, we have shown that a Higgs scalar and a Stueckelberg scalar can coexist in the same theory without any obvious contradictions. The presence of the Higgs scalar helps to break the mass degeneracy between the photon and the Stueckelberg scalar. The Arzai gauge gets automatically fixed. It's a nice bonus. We don't have to plug it in by hand. If you take the delta going to one limit, the unitary gauge comes back, the photon mass goes back to EV, whatever it is, and Stueckelberg terms vanish. Now there will also be new interactions here between the phi and photon and sigma, which could be explored in principle. And if these interactions are weak enough, then your sigma, you might think of that as eventually giving you a dark matter candidate. Okay, now this of course has to be explored. We have not done that. But now, of course, this is a toy model. We now want to see what happens in the electroweak model for which this was originally designed. Now, one thing, you cannot simply add a Stueckelberg scalar to the standard model. All that it will do is it will make the photon massive. So we need to go beyond the standard model if you want to add Stueckelberg. So we look at the next possible extension, which is a U1 extension of the standard model. And here you use the gauge group with one extra U1. Now these models basically give you an extra Z boson, a Z prime boson. And that has been very much in the news because it's one of the things which tries to explain the number of the flavor anomalies. It is true, of course, that flavor anomalies do come and then disappear from time to time. But in general, an extra Z boson has been one of the favored models for explaining these flavor anomalies, and it has to be massive. So let's see what happens if you take a simple scalar. Now, what happens to your scalar Lagrangian? You have your usual, this is the usual one, which comes in the standard model. But now, in addition to the B field, so this is the W fields, in addition to, or I've called them A here, the W fields, you have to add on another. There's a new gauge boson here. And of course, this is your potential. So the covariant derivative also picks up an extra term here. And I write this as all of this thing together as a W mu. And so this is my W mu. And I'm just scaling the extra coupling. So instead of one G prime, which is what is used, I'm calling it Gy and Gx. There are now two G primes. Okay, so now the ratio with the standard G2 is my standard electroweak coupling, the W coupling. So now this is the form of the mass matrix. So I have now these two extra terms in addition to what I get in the standard model. And again, I have rewritten them simply. So these, of course, are the W plus and W minus. And I have just kept these as they are. Now the point is that after spontaneous symmetry breaking, the masses arise from the usual Seagull terms like this. And if you write them out in full, that's how they look. The W plus W minus give me my usual half GV squared. Now here it is half into half GV squared times a mass matrix like this. So these are the new terms. See, this is what you would get in the standard model anyway. It will give you the Z and the photon. But now you have an extra row and an extra column because of the C. So if you diagonalize this, the eigenvalues are the following. There is one which you can, so this part is you get in the standard model anyway. You get an extra term here. The others are both 0. So what is happening? You identify this with the Z, this with the photon, but this one is the Z prime, and it's massless. So the symmetry actually has broken from SU2 cross U1 to U1 electromagnetic cross another U1 extra. So this is the extra U1 is protecting the Z. It's preventing it from getting a mass. So now, of course, we need some mechanism to give mass to the Z prime boson. So that's the core of basic question. So obviously, one thing you can do is you can introduce another level of symmetry breaking. And so, if the Z mass is due to some more symmetry breaking, that will introduce the addition of some more Higgs-like scalars and some extension of the Higgs sector. And this is the popular model. This is there. So I've taken this from Langacker's review. And you see here that symmetry breaking is due to an SU2 singlet and 2 doublets. And then you do some complicated stuff. You get formulae. But you can break the symmetry this way and give a mass to the Z. Now the question we are asking is, can the Z mass arise from a Stueckelberg mechanism, which doesn't break the symmetry? So in some sense, it's more economical. When you don't break the symmetry, there are many operators you don't have to write, which are not permitted. So can we do it from the Stueckelberg? It's just a question we could ask anyway. All right, so let's do that. So here is my full U1 model with everything, same as before. But let's look at the transformation of the U1 gauge fields. So this B goes to some B plus del mu with a theta y. See, I'm looking only at the U1 sector, which I'm already comfortable with. Stueckelberg for non-abelian leads to all sorts of problems. And then the C goes to a del mu with the theta x. So I can add a Stueckelberg scalar which transforms as theta y, but with an my and a theta x. These don't have to be the same at this stage. They could be different. And we'll keep them different unless we have to set them same. So let's do that. So the gauge invariant constructions as before, I construct the gamma and the sigma. So the gamma will now have 2 extra terms instead of 1. The sigma will also have 2 extra terms instead of 1. All right, so the Stueckelberg interactions, again I will add this to the gauge part. So they are as before, gamma mu and sigma squared, and with these two, and then this lambda 1 and lambda 2 are the new things, like the toy model, which come with. And this m is a third mass, which is not related to those others. It's not needed. Those are gauge, in a sense, gauge parts of the gauge transformation. This mass is what I would originally expect. Originally, this was the photon mass. So in principle, these are all different, and let's see how that goes, how far that goes. Now, after symmetry breaking, usual story. So we get Stueckelberg mass terms. Basically, when you replace this by v squared and this by v squared, you get these as your Stueckelberg mass terms. So let's expand them. Again, we need this canonical kinetic energy term, so let's renormalize the sigma. And here again, it becomes a part of this with the lambda 1. And the free scalar part looks like this. So remember what I've done as before. I took the z and I plugged it into whatever was the coefficient of sigma squared, and I get this. So you see, it's different from m because lambda 2 and lambda 1 are not equal. Okay, earlier remember I had to take lambda 1 equals lambda 2. Here I will not get that constraint, and we'll see in a moment. So of course we are worried about the bilinear terms. Let's see what happens there. So now these are the bilinear terms, one from the sigma term, gamma term, and one from the. And now you see here that the coefficients are not quite the same. There's a lambda 1, lambda 2, then there's a different factor, m. So you want these to be the same. See, you want these two coefficients to be the same. You also want these coefficients to be the same. Only then can you write them as total derivatives if you want to get rid of the bilinears. So what you do, I've just copied the previous expression. So I want this part to be equal to this and this part to be equal to this. So let's remove everything else and equate them. So now from here, if you look at them, you can simply divide. You will get my by mx and you will get mx by my here. The m squared, all the lambdas, everything cancels out. So this tells you that mx and my have to be the same. I mean, there could also be a minus sign, but putting a minus sign in the m is the same as absorbing in the thetas, which is the gauge function.
Why would the minus sign become plus sign?
Which one?
In the z
It's just a redefinition of the lambda. So it's just how we had done the model. So you could do it. You could absorb it in lambda. So as you will see, okay. So this mx and my they have to be equal. Okay, and I'll just call it m prime now. No use calling them by different names. So now what will happen? See, the bilinear terms can be removed if you make this assumption, and there's no constraint on the lambdas. Unlike the toy model where we had to take the lambdas equal, here you don't have to take them equal. They can be different, and that will be very helpful in the model. So now look, if you look at the gauge fixing terms, you get an overall, but now you have this nice whole square business here inside. So let's look at it as a diagonalizing problem. So you want both the, so you define two new gauge fields, B tilde and C tilde, which are the orthogonal components. And now your gauge fixing, you have this B tilde, this picks up a gauge fixing parameter. This term doesn't appear, of course, this is a whole square. So this term doesn't appear, I've just put it in my hand and said this goes to infinity. So the C field, you're still in the unity gauge so far as this is concerned. So yeah, one remains fixed by the model parameters, and the gauge fixing is done by lambda 2, remember. The other one is, the mass is fixed by lambda 1. So there's an alternative, you could do it the other way around. Suppose you somehow dreamed up these gauges. If you fix these gauges, then the bilinears would cancel and hence you would get a physical model. So this is an approach taken by, in this paper, by Kuzmin and McKeown, and they had this approach. So unfortunately, they wrote this paper way back in 2001, and they didn't pursue it any further. Now, subsequently, people have done some work, some phenomenological work with, but in those models, they didn't bother about bilinear cancellation. So those models actually are plagued by bilinears. And so they can't be right. And then therefore, of course, if you don't take the bilinears, your mx and my are different. And you can play with all those parameters and fit things, but it's wrong. So anyway, let's write down the neutral gauge boson mass terms. So they look like this now. So why do we get these A's and B's? See, these are linear combinations of the, see earlier I had these two, gamma y and y phi. And of course, phi is that these are the quantum numbers of the scalar doublet. So you'll get these combinations because now I have taken the b tilde and c tilde. So these are things which come in. And now if you look at this mu squared here is the Stueckelberg mass contribution. See, this comes entirely from the gauge theory part. This is the Stueckelberg contribution. It has the lambda 1 in it, also m. So let's look at the eigenvalues. So this has a 0 eigenvalue, fortunately. So the photon remains massless. And here are the other two eigenvalues. You can write them in terms of the a naughts and b naughts. So basically a combination of these. So it is positive definite, has all the nice properties. There are two. One is obviously larger and one is, this is sum of squares. So this is positive. So one is clearly bigger than the other. And you identify them with the Z boson and the Z prime boson. And generally you would like the Z prime boson to be the heavier one because we haven't found it. So let's take this and identify the lighter of these two with the minus sign to be the Z boson. So let's take the M minus to be this. So now if you do a little bit of algebra, you will get a relation like this. This equation is consistent with this mu cos square theta minus 2 and this one. So there are two possibilities of how to implement this. One is set a phi to 0, and then that will, you set a phi to some finite quantity, and then whatever you fix there, that will fix your mu. Your mu gets fixed. Now the problem with that is that if you do it, you will not get the right charge operator. You will get some strange charge for the Higgs scalar. So we discount that. But the other option is to just set a phi to 0. And you set these b phi to 2, b phi squared to 2 tan squared theta w. In that case, mu is not determined. The mu, which is the Stueckelberg part, can remain how it is. So we make this assumption and go ahead and see what you can get. So now the mass matrix, of course, because A has become 0, simplifies greatly to a simple thing, and I have replaced the a phi and b phi. So now you can identify there's 1 0 mass, so you get these two masses. One is for the Z, of course, usual one. That's how we set it. And the mz prime is this. So it's related, it's clearly non-zero, and you can make it large by choosing m large, for example. So and this is your scalar mass. And as you can see, both have the same factor in the numerator. So the scalar mass can be related to the Z prime mass by using this, so that they are nicely related. So both of them will grow with m, and they will also grow as lambda 1. So here is a graph which shows you a scatter plot. The scattering is because of different values of lambda 1, and this is the line mz prime is root 2. So as you see, your mz prime can be quite heavy, up to drawn it up to 2 TeV, and m sigma up to 2 TeV. Beyond that, it just follows this equation. So the other term basically drops out. Now, what is the advantage of this? The physical fields are these. After you've done that diagonalization, the Z, which is the normal thing, but with the C mu, this is where the photon used to sit, and the B field used to sit in the standard model, and similarly with this one. And the Z prime is this B combination. Okay, I could have written it the other way around. I could call it C and B tilde if I wanted to. But what is interesting is that the first two equations are very much like the same mixing as you get in the standard model. And this is a new gauge field. And the specific gauge fixing, if you remember, happened only for this B tilde field. So that's happening for this new physical field. The other one is unitary gauge, which is what we said in the standard model. And of course, these two new particles, the Z prime, and these are the only two new particles in this model, they grow heavy together. So you can, of course, avoid all experimental bounds by saying they're very heavy. But let's see what it is. So now the next thing is that if you want to write down the interactions, you need to choose the quantum numbers suitably. So let's rewrite the covariant derivative for an SU2 doublet, same one as before in terms of the physical fields. So now I put physical fields Z, A, and Z prime, and those charges are defined here. These are the charges. And the charges are written in terms of these A and B's, A's and B's, and here are the A's and B's as defined earlier. So this part is very standard model-like. Okay, if you put B, for example, equal to the standard model value, you will get simply the standard model. So this is, and anyway, we know what the couplings of the Z and the photon have to be. They have to be the standard model couplings because they've been well measured. Now, for the scalar, however, in this case, Remember, we already set A phi. This is for any doublet, any A, any B. But for the Higgs doublet, we set A phi equal to 0 and B phi equal to this. And the result is that you see, the Higgs doublet decouples from the Z prime. So otherwise, the Z prime would contribute to Higgs measurements. It doesn't. However, it can still couple to fermion doublets. And let's look at the couplings to fermion doublets. So the independent parameters, let's take them as Gx and Gy. The Higgs doublet is now, these are the quantum numbers. So I could have taken the quantum numbers as something fixed and adjusted the couplings. I have done the opposite. We could have done it either way. The results would be the same because they always come as a product. So anyway, the quantum numbers are fixed. You can use these to write the A and B in general in terms of the Higgs. And now here the charge operator must match with the charge operator of the standard model because of course QED is measured to get precision. So that gives you this particular value of B. In terms of Y, this is the hypercharge you have to give to the doublet or the singlet in the standard model. So the standard model value, and the A is given like this. Now if you look at this, so YSM is known to us. So and here the couplings are given by A and B, and you have only one unknown, which is the Y assignment, the hypercharge assignment, the first U1 or the usual U1, and see that's the only assignment to make. So we have to worry about. Now how do we make the hypercharge assignment? Of course, there is a constraint for fermions. When you look at fermions, you have to worry about anomaly cancellation. And of course, we know that for the standard model, we do get the anomaly cancellation. It does happen. So what we require is something similar. We want this to happen. The AF, sum of AFs and sum of BFs, at least over a generation, should be 0. So when we make this demand, so here we are. So you see, this of course is 0 when you sum over AFs. This is 0, BF is taken care of. There's this YF to worry about. So you have to choose YFs in such a way that the sum over a generation is going to be 0. So the simplest and cheapest choice is to take it proportional to the standard model couplings. You could take other choices also. But this is the one which works best, and that's what we do here. We simply take in some eta parameter function, so some eta constant. And so if you take this proportional to YSM, you can pull YSM out. Whatever you get here is proportional to the standard model. So now anomaly cancellation is automatically taken care of, but you didn't have to do this. You could have made another choice possible, and if they would could. So we have a plan that we will look at other choices which are there in the literature and use it to explore favor anomalies. But the anomalies have to last till we do the calculation. However, we'll go ahead with this. So this is now a 6-parameter model. So what are the models here? There is this general mass scale. And then there are the Gx and Gy, which are the new scales, and lambda 1 new quartic couplings. And we have perturbate. So notice that all of these, why choose these as parameters? Because they all are limited by perturbation theory. They can't be too large. They can be small, but they can't be too large. They can't be too large on the negative side either. Okay. So now I'm well in time. So we can use this now. I mean, not going to derive the Feynman rules. You will have couplings between Higgs sigma sigma, Higgs z prime z prime. I haven't written the unphysical Higgses. And in terms of these parameters, you scale the z prime. These are all dimensionless parameters, the A, B, C's, and so on you get here. The dimensionless parameters are this zeta prime, which is the z prime over v squared, scaled to the standard model. And these A's are all in terms of this dimensional, the lambda 1, lambda 2 couplings and this zeta prime. So you can work it out. Now, this is fine for the bosonic sector. For the fermionic sector, the couplings look similar to the Z boson coupling, except that the vector and axial, so that this eta factor which will be sitting outside, which of course we know. It came from the hypercharge choice. So this eta factor is an overall factor, and this is a little different. It's not exactly the same factor. For the Z boson, you get 1 by 4 cos squared theta w, and this is root 2, so it's certainly a different factor. But these are also different from the exact Z boson couplings. And what they are all given here. You can write them in terms entirely of the standard model couplings. That's how we chose them. So 1, 3, minus 5 by 3, 1/3, minus 1, minus 1. So similar, but not quite the same. So we now know these couplings, and here's a plot of these couplings. So if you want to see how they vary with eta, see eta is the crucial parameter here. It fixes the size of whether these couplings will be large or small. So if you look at this plot, let's look at the left one. Well, let's look at the charged lepton. It's the most important one. So you see the dashed ones are the couplings of the Z, the normal Z which exists. And here are the couplings. So you see that eta grows a little bit, okay, then these grow very fast. So there's a big deviation from standard model. Standard model, the vector coupling of Z is almost 0 to charged leptons, and the axial vector coupling is at -1. But these can become very large. And a similar phenomenon happens in the others, but as you see, it's most marked among the charged leptons. And so the charged lepton are the good ones to look for deviations from the standard model. They're the most obvious things to look for. So we did that study. So the charged leptons, our best signal would then be contributions to this is your Drellian process. So 2 protons collide, 2 quarks, and then you can have a production pair of leptons, and here are this is your Z prime contribution. So there's an interference with the standard model, and when you compute this, then of course the Drellian is very well measured. These leptons give you very clear signals at a collider, very easy to measure. We mostly measure electrons, electron pairs and muon pairs. So there are stringent bounds, and there will be more and more stringent bounds as the LHC keeps running, or any future hadron collider will of course look at this process. So we did a study of that. So we worked on the Drellian cross section for dimuons, and you see here the standard model is here, and you could get large deviations for eta. And the interesting thing here is that if you see, you should wonder why this is not growing with eta. That is because there are interference terms with the standard model. So as you go to larger and larger values, these interference terms start dominating, and there's a cancellation. So they fall off as you go to larger energies. And this is for different values of the mass, of the Z prime mass. So as you see that when Z prime is about 300 GeV, which is sort of at the threshold of observation, then you get very large deviations. So these are sort of ruled out by the standard model, by the experimental data, but it falls off very fast. So by the time you have reached 700 GeV, you're only a little bit above the standard model value. And so we use that to predict 3 sigma discovery limits in the LHC. The red one is what exists. So the larger MZ and the eta on either side are the predicted ones. So for different values of eta, MZ below the line is ruled out. So now it's here at the red line. And then as you collect more and more data at the LHC, it will go up, eventually perhaps up to here. And so you will probably, at the moment, even in the sort of highest place, we are probing about something like, 2, 3, 4, 5, maybe 500 GeV. So it's not very strongly ruled out. But as we go to higher luminosities, the model will be probed. And it can be probed as high as about 20 TeV. But on the other hand, there will be a possibility of something remaining in this hole up to here. And so we will perhaps have to look at complementary signals. We have not done that study yet. But this is, as of now, the first how should I put it, the first point of attack of the theory. All right, so I finished very well in time. Conclusions are the following. The Stueckelberg method is an elegant way to give mass to a gauge boson without breaking the gauge symmetry. I introduced that. The unbroken symmetry, this is important, it prevents many operators from appearing, and so it makes the model economical. The number of couplings is limited, number of extra particles is limited, so it is predictive. It has been applied before to a U1 extension, and as I told you, it has been applied sort of uncritically without looking at to see that it's a good field theory. So what we have done for the first time is to study it carefully. We've taken care of bilinear cancellations, gauge fixing, anomaly cancellation, and ensured that the charge terms have the canonical values. So with all of this, we found a viable 6-parameter model have been created. It has good testability, as we just saw. And the preliminary collider studies have also been done in the LHC context. We plan to look at it in more detail afterwards. So thank you.
Okay, questions?
Nice talk, Sreerup. There was an issue of unitarity, was it not?
Yes.
With even the Pauli
Yes.
modification.
Yes, that issue survives. I mean, see, you have derivative couplings. So unitarity will always be a problem. So at the moment we have brushed it under the rug because most of the other work which is happening in electroweak physics today uses effective field theories and nobody worries about unitarity. But yes, unitarity is a question. So one of the things we would want to look at is that where, at what scale unitarity is violated. So we are not claiming that the Stueckelberg scalar is the theory.
Yeah, so it does not have the same status as the standard model as a fundamental theory. If you want to have an ultraviolet complete theory, this one certainly doesn't. If you have the Stueckelberg.
That is true, but the standard model as a complete theory has its own problems.
Yeah, okay.
And that's why, so that's why people are looking at effective theories with, high dimensional operators and so on. So right now, unitarity is perhaps not the biggest buzzword. Okay. So we took it in that spirit, but yes, there is a problem with unitarity. That's very well taken, yes.
I had another question. You have, of course, an extra Z prime boson because you have an E1 extension, which also means that you will have more neutral currents. What about flavor-changing neutral currents? I mean,
so that's the whole point. That's the whole point. So of course your Z is heavy. See, flavor-changing neutral currents occur at low energies.
Right.
So if the Z is sufficiently heavy, you will not see any effect there. However, we are hoping that the Z is on the cusp, where it will give you some small effects, and those are the small effects which will explain the flavor anomalies. That's why I kept saying that we will look at the flavor anomalies and see what it gives us. But by the time you start doing a flavor anomaly in detail, it disappears from the experimental results. So that's been happening over the last few years. So we don't know. I mean, we have to see. So this follows whatever the experimentalists tell us.
Any other question?
Yeah. Yeah.
If you took a complex scalar, I mean just a usual Higgs mechanism for a gauge boson, and you keep the expectation value fixed and let the scalar mass go to infinity, the Higgs mass go to infinity, would that not recover the Stueckelberg mechanism?
I suppose that would happen. Yeah.
Okay. So then, if you have unitarity problems, it's due to this thing becoming infinite, I suppose.
Yes.
Okay.
Yes. See, these are things which were known. So what we are trying to do is revive it without worrying about unitarity, because today, as I said, nobody really worries too much about it because yes. 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 We'll wait for things to happen. That's the philosophy. But that's the way most electroweak phenomena is being done nowadays.
Any other questions?
Yeah.
So I couldn't tell if rho parameter is, corrected.
Rho parameter won't be correct because see, the standard model part essentially remains the standard model. None of the standard model couplings are affected, partly because we set the charge operator to the standard model value. That resulted in the Z1 also being set. So the standard model part is unaffected. You only get these new interactions. So there's the rho parameter and all these other oblique parameters, all the standard tests are all protected.
So that is at tree level though, right? I mean, if you do loop corrections, would you still maintain that to be 1?
No, but at loop corrections, then unitarity comes into place. So
yeah, true. But independent of unitarity, at least you could ask about rho parameter contribution.
Yeah, so rho parameter, tree level, there won't be contributions. There'll be high level contributions. So we have to see. That we have to see. The loop corrections are at all anywhere close to the experimental thing.
Okay, then if there are no further questions, let us thank Sreerup for a very nice talk.